Hi mechanics friends, I hope you're ready to continue calculating bending stresses and beams. It's such a great adventure out there in this world. Anyhow, let's orient ourselves to the problem. This problem is a lot like the last one, so let's go through it. The member here, though, is made of carbon fiber. One of the cool things about carbon fiber is that it has different capacities in both tension and compression. So we see it has an allowable tensile stress of 600 megapascals, while in compression it can only hold 570 megapascals. Now we're asked to calculate the maximum distributed load that can be applied to this member. So let's go ahead and think about the stresses that are acting on this cross-section. We see that due to the applied load, that'll create a bending moment that will lead to tension on the bottom and compression on the top. Now I think you have enough knowledge to go ahead and solve this problem on your own. So I would say go ahead and pause the video here and give it a try. If you're not really sure where to start with this one, I would recommend going with the shear and moment diagrams. That'll give you a value for the moment that you can use in your sigma equals my over I equation. Well, hopefully the problem went well for you, but if you had a little difficulty, let's start with the shear and moment diagrams. So I've just noticed I've kept them in variable form here. So keeping them that way, we can get to the maximum moment. The maximum moment here at the center of the span is going to be omega L squared over 8. We're going to apply the same bending stress formula that we've learned. So that is sigma equals my over I. And I'm just going to write it out for both the tension and compression cases. Again, remember tension is going to occur on the bottom of our beam. So when we look at the distance y in our formula, y is going to be the distance y to the bottom of the cross section. Whereas when we look at the maximum compression stress, we want to use y to the top of the cross section. And that's all relative to our neutral axis, which is shown by the dashed and dotted line there in the center of our cross section. So if you haven't finished solving this problem yet, go ahead and pause the video here now and try to solve at least for the center of gravity and the moment of inertia for this cross section so we can get y and we can get I. Hello again. So hopefully you found successfully the center of gravity and the moment of inertia about the neutral axis. But if you had some problems, go ahead and take a look at these calculations and hopefully they'll make sense to you. Now, if you want to set up a table again, like example 3, go ahead. But if you just want to write out the formulas, hopefully you'll follow along with these calculations. So this is just kind of doing the contribution of each segment. So here I've taken the contribution of shape 1, which is in blue, and now I'm taking the contribution of shape 2, which is in red. And I'm just going to go ahead and just put them directly into the equation instead of creating the table. Both are perfectly fine. If you like the table better because it gives you a nice method to solve this problem, then of course go ahead and use it. But if this kind of just using the formula and writing it out makes more sense to you, then this is also the same calculation, so go ahead and use those. So now using these values for y bar and the distance y top and y bottom, as well as the moment of inertia, now you have y and you have I. You also have m from your moment diagram, and you also were given the maximum allowable tension and compression stresses. So you pretty much have everything you need to solve for omega. So if you were a little bit confused earlier, now that we have these numbers, go ahead and pause the video one more final time and try to solve for the maximum allowable omega for both tension and compression cases. Alright, so now we're going to figure out what the maximum distributed load allowable is on this beam for both tension and compression. So I'm going to separate the two cases because remember, we had different stresses allowable in both tension and compression. So I'm just going to go ahead and divide the page into two. I'm going to use the bending stress equation, sigma equals my over I. Now the maximum allowable stress for tension was 600 megapascals, which is 600 newtons per millimeter squared. I'm going to set that equal to, remember from our moment diagram, we got the moment to be omega L squared. L was 5 meters or 5,000 millimeters squared over 8 times y, the distance from the neutral axis to the face of tension, which was y bottom. So that's 186.538 millimeters. And I'm going to divide that by I, which is 73.097 times 10 to the 6 millimeters to the fourth. As you can see, I have all my units here in newtons and millimeters. And so what that will result in my answer and my distributed load being in terms of both newtons and millimeters. And so solving for that, I get the maximum distributed load in tension allowable is going to be 75.24 newtons per millimeter. We'll repeat the calculations for compression. So again, sigma equals my over I. Everything will remain pretty much similar except the maximum allowable stress for compression was only 570 megapascals. So that's 570 newtons per millimeter squared. And then the other change is that we need to use y to the top of the cross-section because the top of the cross-section is the portion of the cross-section in compression. So y, the distance to the top, is only 63.462 millimeters. M is the same for the beam as well as I. I is always about the neutral axis, and it remains the same for both the tension and the compression side. So running through these calculations, we find that the maximum allowable distributed load for compression calculates to be 210.09 newtons per millimeter. Finally, we have to decide which one is more critical, so which one causes the beam to fail first. So when the distributed load gets up to 75.24 newtons per millimeter, that's when we would first have failure. So we say that tension controls. All right, so flipping back to our previous page, we can go ahead and take a look at the state of stress in the cross-section if you would like. This wasn't specifically asked for in the problem, but we can go ahead and take a look at it. So I'm just going to rewrite some of the values we had for the distances. So the distance from the neutral axis to the bottom of the cross-section was 186.538 millimeters. The distance to the top was 63.462 millimeters. And we said that the tension controlled, so that means we reached the maximum allowable stress and tension, which was 600 megapascals. We know at the neutral axis we have to be at 0. So, and we also know that sigma equals my over I, which is a linear distribution of stress in the cross-section. So plotting a straight line through 600 at the bottom and 0 in the middle, we then can get to the top value for sigma compression. All that's left is to do a simple similar triangle to figure out what the value is at the top. So we do 600 divided by the distance, 186.538. That has to be the same proportion as sigma c divided by 63.462. So calculating sigma c, we find that sigma c turns out to be 204.22 megapascals. We can go ahead and sketch in our stress, compression on the top, tension on the bottom. That brings us to the conclusion of this problem. Hopefully you were able to calculate the values for omega without too much difficulty, and that you're becoming more confident in your ability to calculate bending stresses in members. In the next example, we're going to combine these bending stresses with axial stresses. So I'm looking forward to that next adventure with you in this ocean of mechanics.